That's not coming up on the screen for some reason. Why is that? But I can do that, but it just...
There we go. Now,
Yeah.
now you go. There you go. That's it.
How we doing? Yeah, about. Getting into the island itself. Can you all see that one? Yeah. You've disappeared. Yeah.
Well, that's okay.
Yeah, you can hear that and see that, right?
Yeah.
So this is let me just get my laser printer out, laser pointer. This is where I am in the north here, and as I say, it's about 30 miles long and about 15 wide. This is where you would arrive in Brodick, and you would work your way. There is really a coastal road that goes about 59 miles all the way around the edge, generally on the raised beaches. What you will see from the pictures is that that this red area, it is our granite up here. And I apologize because this is a photocopy, if you like, picture, so the printing isn't quite so clear, but that's the granite, and it's 60 million years old, and that's where most of the higher peaks, ranging from 600 meters or 2,000 feet up to about nearly 3,000 feet at 874 meters, which is Goat Fell, which is kind of here, and you would see from the ferry as you came in. That's a huge granite diapir, which is like a balloon, and there's another area around here which we'll talk about a little bit later on, which is the Central Igneous Complex, which is the posh name for a volcano there. So that's the volcano, similar age, give or take a few 100,000 years to this. But as I say, we're going to start off in the north here, and you will see that there's a yellow zone all the way around the edge of the red part of the granite, which are our oldest rocks there. And so this is what we're going to look at. So Arran's rocks span about 550 million years of age, which means that Arran's oldest rocks on the ground are Cambrian in age. Although, as I will say to you in a minute, we often refer to them as the Dalradian, because these rocks here and others across on the mainland just over here, which is the Kintyre Peninsula, they belong to an area of Scotland which was known as Dalriada, and it was the ancient kingdom of Scotland. So they called them the Dalradian, but they actually span from about 700 million years to about 550 million years. And of those, Arran's rocks at 550 million are the youngest, just here. But on Arran, generally, as I've tried to say, we go from our oldest rocks there right the way down to the Triassic rocks, which are the youngest rocks that we've got in any large number, although there is a nice little hidden secret that in the old volcano there, we do have little bits of Jurassic and Cretaceous, but they're only about as big as your front room that you're sitting in at the moment. So they're not big, but they're important. Separating the north there from the south is a major fault, which kind of comes more or less around in this area, and in other parts of Scotland that would be called the Highland Boundary Fault. So that would be that one. So as we said, Arran is really a land of contrasts, much like Scotland. In fact, you'll know geologically we often talk about different terrains and or sort of landscapes made up of different types of rocks. And I suppose in Arran we've got two different types of terrain. We've got those in the north of Arran, which are greatly folded, as you can see, and those in the southern part of Arran, the other side of the fault, Highland Boundary Fault, which are generally sedimentary. So looking at the north of Arran, and this is not too many miles from where I'm seated, you will see that a lot of the rocks here are very, very thinly layered, or as we would say, laminated, almost like the sheets of paper in your daily paper. They're about 1 millimeter in size, but you will see also some thin units there, the lighter coloured sands. Now this is an area, this slide is an area where we've got a lot of very fine material compared with coarse. We do have some coarser material in the older rocks, but this is particularly, of course, you get the much better exposed folds. You see a lovely fold axis running through there. You get the much more detailed folds in the finer rocks rather than the coarser rocks. And you'll see this old sea stack on the coast road here, where you've actually got the folds actually wiggling in and out, all in the north. So, as I already said, and this was kind of summarising it, Arran's oldest rocks are Cambrian age. They're the younger part of what is locally known as the Dalradian. Remember the ancient kingdom of Scotland. They were deposited over a 200 million year period in this basin, and they were deposited, which I didn't say, and I'm going to show you in a second, between an area of Scotland which is the Great Glen Fault, which many of you'll know if you go about 60 miles north of where I'm seated, you'll be up at Oban, and about 100 miles north of where I'm seated, you'll be up at Fort William. And that fault really runs from Oban through Fort William and right the way up towards Inverness. The rocks themselves, when you start to try and get clues from the oldest rocks on Arran, more difficult to see. One thing I should say to start off with is that if you do a scratch test on them, you know, just running a nail over it, you'll find that a lot of them are very fine and made of clay and are quite soft. They're also kind of greenish blue because they've got the mineral chlorite in it, which is, those of you know about regional metamorphism, they're kind of the lower grade regional metamorphics, typically suffering about 5 atmospheres pressure and about 400 degrees centigrade. But they were deposited originally as sediments. And this is a nice example from a stream bed with the water over the top, showing a little bit of graded bedding here, where you've got the coarser bits of quartz and that grading in that direction. And this graded unit was typically laid down by turbidity flows. Okay. So the idea for Arran's oldest rocks is that, if you like, we would probably have something like the Great Glen Fault here, and north of it, of course, other Cambrian rocks are when you get up to the Northwest Highlands, and you get all your you get your limestones, and you get stromatolites, and you get sandstones, and that was probably the coastline, the near coastline. And then you had, coming off those lands up in the top, you then had lots of sediment building up on what was then maybe the continental shelf. Before you had a bit of maybe earthquake action, one would imagine, you know, because of what we'll talk about, this continental collision, and all of this loose sediment on the continental slope would have then plunged down very rapidly, forming these huge low bait type fans, like alluvial fans, but underwater. Many of you possibly know, the east coast of America, in the old days when we had the telephone lines across the transatlantic, they were affected by turbidity currents like this. And I was talking to a researcher from Hull University who's been looking at similar fans off Monterey, on the California coast. So deep sea sort of turbidites. Now the whole idea, and this is just a model, for it, but if you imagine on this diagram here, this is roughly where we probably are on a block model. This is where Arran is. And there is some thought that at one time this might have been a volcanic arc where Arran was. And there was a basin behind us, behind Arran, and going up to the Great Glen Fault. And so these were all where the Dalradian was deposited. And most of the material was coming in from the north on the Laurentian plate. Remember, Laurentia was, if you like, America and Norway and Scotland. And then way over to the right on our screen, we've obviously got Avalonia, which would be where England and Europe are. And these plates were gradually coming together, and this basin of all these soft sediments was then later going to be rocked up into very large folds. Notice here we've got what's said to be NGS, that stands for North Glen and Sannox, and haven't got any pictures here, but we do have some pillar lava structures which are Ordovician in age that were formed around here. And those of you who've ever been up the east coast of Scotland, west coast of Scotland, but a little bit east of us on the Ayrshire coast at Ballantrae, will know that we've got a very famous ophiolite there. All right, which for those of you who don't know, that's where you've got a section of oceanic crust with pillar lavas, black shales, underneath it sheeted dikes and gabbros, testimony of ocean floor. So there's some interesting rocks in this area. But this was the sedimentary environment, so a kind of sea basin beneath an island arc, if you like. Most of the sediment coming in from the north, a little bit locally coming in from the south where Arran was. So we were there, and all of our ones in Lochranza probably came quite locally, falling down these slopes. If you ever go on Earthwise and have a look at the BGS and have a look at the models they've got for the Caledonian orogeny and the Caledonites, you will see that our part of the world here, about 420 million years ago, was subjected to multiple crashes, really. We had Laurentia, but closing in from the east, Baltica, which was squashing this way, but coming in up towards Scotland was Avalonia, with a little bit of the ocean Iapetus between. And so we had then a situation where these sediments were all deposited in layers up to 10 kilometers thick, 6 miles worth of thickness of sediments. But then if you imagine that we're going to push the plate from Avalonia in here, and we're going to push a bit harder than pushing from Laurentia in here. So we actually start to get an asymmetrical fold, which then, like this, and this is the evidence, just literally a few hundred meters down from where I'm seating, you can see these. Now, I apologize, there's not a scale on this, but these are only quite small. That's about 30 centimeters, about a foot. And you see a lovely axis of a fold there and an axis of a fold there, but you see the typical Z shape where we had pressure coming more on this side than this side. And then I used to like wearing a t-shirt that said it's not my fault, I just can't take the pressure. And there is a lovely bit of metamorphosed sandstone here, which is about 10 centimeters thick, and it's bent over like a large banana coming back on itself there. So you've got a large overfold. Well, I say large, it's only about a meter in size, but it's you know, a bit bigger than some of the small stuff we've got. So it's bent over on itself. But you notice the bottom part here, whereby the lower layer of the sandstone there was originally there, and the upper bit there is now over there. So we've got a mini thrust fault there, and we've got an overfold, and you will see also in here a little bit of fault breccia running down here, and sometimes, maybe not on this slide, sometimes you can see the Z-shaped bits of the sand. Remember, this is a mixture of mud and sand, so the dark bits are the mud and the lighter bits are the more resistant sandy layers. So the idea was that the area that we've got for Arran, if you like, were and all of the mountains that gradually formed this side of the Highland boundary fault was as Avalonia came in this direction and met Laurentia from this, all of these soft sediments were folded and overfolded, so that you originally had 6 kilometers worth of sediment, but they were the crust was shortened and thickened in that area. And for those of you not seen it, this is a lovely picture that you can get off the BGS website and Earthwise, but it shows the structure in this area, whereby we've got a very large banana-shaped structure, or what we would call as a nap-like structure, and you notice it's bent over, and the very nose of that fold just there, which we locally know as the Aberfoyle anticline, you would say, well, hang on a minute, that's shaped like that, so it's a sin form. And it is a sin form, but actually a sin form describes the shape of it, so it is a sin form, but actually geologically, because it's been bent over, and these are the oldest rocks which are inverted on the bottom, that means that the youngest rocks in here are in the core, and that's the definition. That the oldest rocks are in the core, which is the definition of anticline. So it's actually a sin form by shape and an anticline by structure. And that's the Aberfoyle anticline, which just touches base into Arran. So all of our rocks on Arran are actually this part, and they're all upside down. All right, except when you come out to North Glen Sannox, and I showed you that slide there of the graded bedding, and that's actually just this bit, which is the right way up. But most of the right way up these days has been eroded away. Notice also that with the descending slab of the apatus going down, we've got melting of that slab, and we've got all of the granites that you're typically used to when you come up to Glencoe and Rannoch and Ben Nevis, all associated in Cruachan. I'm sorry, we've got a demented cat at the moment, so apologies for the sound effect. So we were talking about terrains, and we were in the Grampian terrain when we were up in this area. But then when we cross over the Highland boundary fault, as maybe, it could be an unconformity on Arran. It could be a fault, but it isn't certainly a big topographical feature as you see in many parts of Scotland. So you've got a junction here between Devonian rocks that are about 400 million years old, and actually Dalradian or Cambrian age rocks there. And that's at this point. Now, as we cross over into this area, we then come on to the Midland Valley terrain, which is typically made of Devonian, Carboniferous, Permian, Triassic. We've also got, as I say, Jurassic and Cretaceous, and then the Tertiary or Paleogene on top. Now, as you do that and come over, you've got a totally different set of rocks. And essentially, if you walk, I'm actually round this hill, around the other side, but if you walk around this coastline and about 2 miles, in the space of 2 miles, you actually go through probably 200 million years of Earth's history, layer upon layer upon layer. And these pictures are taken of Carboniferous red limestones and shales. And I say, yeah, red limestones. It's always something that gets a lot of students when they come out here. But you've got some nice brachiopods and rugose corals and even trilobites in there. So that's that. Now, in terms of this, I'm just refreshing your memory. Of course, when we go and we come out of lockdown and we're able to travel over our planet, you know that because of the heat flux on the planet and distribution, we've got all sorts of different different heat zones, if you like, going from temperate zones where we are through tropical zones and then equatorial zones. Not only that, but when we go around the planet now, because most of us, well, you know, as a human race, we've traveled most of the planet, we've got a fair idea, a conceptual model of what the planet looks like. So if you like, we might have some high mountains like the Andes or the Himalayas, or even the Grampians for that matter. And off those mountains, through freeze-thaw action or frost crystallization or whatever, we got lots of loose material that's all forming cone-like alluvial fans. When we've got a coalescence of alluvial fans, we often have little thin, shallow streams on the surface, which we call braided streams. And as you come away from the mountains, those braided streams might make more sinuous river systems, such as meandering river systems, and going over lower land. And then we might actually say we might be going through and have deserts quite close by and salt pans close by. And then we hit the coast. And of course, we've got a linear deposit of beach there with, you know, boulders and cobbles and then sand and then mud, if you like. That goes out onto the sort of shelf, the continental shelf. And then, as we saw earlier with the Cambrian in our area, we've then got these submarine canyons where we've got turbidity currents going down there. So that's our conceptual model. And then we start to try and look at the clues in some of the rocks. And in the Devonian, of course, if you went down to the type locality for the Devonian in Britain, in the world, in Devon, you've got actually lots of lovely limestones down there. But in Arran, you know, we've got these. It looks like a builder's yard. And if you look closely, though, you know, there are some clues because there's some really nice cross-bedding in there. And you can see, you know, there is a little bit of sort in there going upwards. Sorry, again, you haven't got a scale here. These are about the size of a splayed hand. So these are cobbles. And then you get into fist-sized pebbles and then up to gravel. And occasionally you get sand lenses before it starts again. The interesting thing about here is that those rocks are dated about 400 million years of age, but some of these particles or clasts within it are dated about 1800 million years of age. All right, so these been around, hence they're nice and round, for a long time before they were ripped up, eroded, transported and redeposited. So it's a really nice example of polycyclic or many cycles of sedimentation for the Devonian. Moving on from the Devonian and following directly on, in the rocks close by those limestones, you can actually find some lovely sea turfs. Now, I don't know whether you've come across sea turf before, but sea turf is a name for Carboniferous fossil soil. And essentially, like with any soil, you know, I was digging our veg plot today and pulling out roots. I've got root zones in there. I might have bits of dead root. I might have twigs and leaves, but it's all mixed with quite a lot of sand and silt. And there's also worm burrows and things like that. So we've got quite a lot of sea turfs, which would typically formed in swamps. I was lucky enough, Mike was telling us earlier that I think, I can't remember, I might have missed out. No, this was the Azores. And it was just seeing this lovely tree fern with all of the diamond-shaped bark there and the scales, which is kind of what you get with lepidodendron. And we've got lepidodendron molds in some of those as well. The other thing that we've got, which is quite famous on Arran, is this track. And Sir David Attenborough visited it with the first of the series of Life on Earth. And he came here and he saw this track, which I think Derek Briggs spotted in about 1973. And it's about 30 centimeters wide with lots of little imprints going along there. And they actually identified this trackway as being produced by this fellow here, which is known as Arthroplora. What you don't have there is a scale. So for those of you sitting on the couch and a bit faint-hearted, this guy is about 1 meter long and about 30 centimeters wide, which automatically puts us in a fight with the zoologists who say, how can you possibly have an animal that size that breathes through his exoskeleton by a method of spiracles? How can that possibly function in our atmosphere? But of course, we've counted and produced evidence that during the Carboniferous, there was a lot more oxygen maybe in the atmosphere than there is today, and certainly enough to produce the first ozone, which meant that the reason this is so famous is because it was one of the first tracks ever made by a land animal on there. So we've got a lovely example of a trace fossil. Unfortunately, I haven't got the picture on here, but one of the profs from Cardiff who studies these guys on the Corrie section, the Carboniferous, just last year, actually found a burrow. And he reckons that at one time, you know, possibly these guys, wherever you find these tracks, you also find burrows. And you just wonder whether he didn't actually lie and protect himself in a burrow. And, you know, it's just conjecture. I don't know, because I'm not a paleontologist, but you just wonder, I wonder when he shed his skeleton, whether he actually did need any protection and therefore he buried himself for a bit. I'm not sure, you know, that's just conjecture. Also in the Carboniferous and testifying for a deltaic type of environment where we've got the swamps with all the coal and the sea turfs and the plant fossils and the coastal area, if you like, and the swamp and floodplain deposits where you've got the fossil tracks. We've also got these, what I locally call Glasgow smiley type structures, which are actually made of calcite. And these guys are the bottom, I don't know whether we can actually see there. There's a lower one there and an upper one there. So this is the bottom and top of a large gigantoproductid. And you remember, productid brachiopods are slightly different from your bivalves, which are like your cockles and mussels, because the shells are not mirror images of one another. So if you take your hands at the moment, palm side up, and put lower hand in there, imagine the upper valve was actually just pivoted on a hinge and would open and close. And you've actually got the lower valve, which was typically known as the pedicle valve, and then the brachial valve above it. Some of these would have little spines on because it's in soft mud. Some of them would also have wings on them. Not a lot of faunal diversity in the Carboniferous, typically brachiopods, arugose corals, the odd goniatite. As I say, we have found some of the Phillipsia, which is kind of the last genus, if you like, of the trilobites. So there is a bit to see. And on mainland Scotland, they actually did find fossil sharks, so, it must have been interesting being around in the Carboniferous seas. And, just to take you away, like you said about the Caribbean, so this was just to give you an idea. Often when I'm standing in the students in hailstones and driving wind and rain, I say, well, you've got to have a good imagination, but imagine that these corals needed about 28 degrees centigrade water. It's hard to believe today when Arran's summer temperature is about 19. So these waters would have been about 28 to have all of these little bioherms, these little reefs, of course, with fish and sharks. After we went through the tropics and the equatorial climes of the Carboniferous, we then came into environments similar to the Sahara today. And you would have had large player lakes and also lacustrine type environments, with typically by siltstones and shales and thin sandstones. And this animal, rather like a sort of Komodo dragon, if you like, a reptile type, was the forerunner of a lot of the dinosaurs. And this is known as Cytherium, or the hand beast. And in some deposits on the south end of Arran, you can see, the claws in the shape of a hand going there. Now, again, I apologise. Well, you can see there a scale. That's a 10p piece. But this track is maybe about 30 centimetres, this print, 30 centimetres from bottom to top. And you can actually find trackways of them. So when I'm ever listening to Simon King talking about from Africa, and you think about the lions lying in ambush by the waterhole, you often think that all of these guys were possibly waiting for smaller prey and whatever that was coming down to the waterhole and maybe ambushing him. So, that's the thought. But Cytherium, I don't think they've ever actually found a full body of this. And they've certainly never actually found a tail print. But if you Google it, you can see lots of prints of the various tracks made by these guys and others during the Triassic. Again, a lovely example whereby on certain sections you get lovely examples of player lakes. The slide doesn't show you here, but down by the shells there's another layer like this, which is mud cracks or desiccation cracks. And there's a layer down there with a layer of sand in between, and then this layer on top. And some of these are rather like poppadoms. You've ever thrown them into a frying pan and they curl up at the edges. They really are dome shaped. So it must have been quite extreme temperatures. Not extreme enough to melt a whisper, but it was certainly warm during the Triassic. Although that said, I had a group out here, believe it or not, I think it was last year or the year before, and in the summer, I recorded, I think it was 35 degrees out there, and I had real concerns for the students who were mapping this area, because I said, you can't go out there for that long. And there was pools of water left by the tide that morning that were turning into salt cones. And I just thought, boy, I've never conditions like that on Arran, So maybe we might see a bit more of this the way things are going. There are some of your large desert sand dunes. Remember, these were Saharan type, and you will see the foresets here coming across like this. So we actually had the wind. This is a paleo wind forecast for this desert 270 million years ago. But essentially, the particles were coming along here, being blown up, and then avalanching down here, blown along here, avalanching down there, and so on. And then the wind changed direction and eroded away at that point, and it probably went in that direction. So these are very large scale dune cross bedding, the sort that you get in places like the Sahara and Namibia. Very interesting. You might not have come across this one before, but you see it's only a small structure, but there aren't too many of them. This one is a fulgurite. It's great for playing Scrabble with, but people deny total knowledge. But a fulgurite is actually a fossilized lightning strike. So you can imagine a bolt of lightning hitting this sand and causing all the grains to weld together into like a little mini volcano. Of course, underneath here, it would be a bit more of a dendritic pattern. I believe Cambridge have got one of these, because obviously geologists have been visiting this island for many, many years, but they've got one of them in one of their museums. Of course, the main thing about Arran, it depends. I mean, there's so much, maybe you've got, if you like, metamorphism, you've got that. If you like sedimentary, you've got it in total gay abandon with all the different environments. But one of the classic iconic things about the west coast of Scotland is all of the tertiary centres. And you've got the Isle of Arran there, you've got Mull there, you've got Rum there, Skye there, St Kilda further north, and you also pass through Ardnamurchan there. All of these were volcanoes some 60 million years ago, and were associated with the so-called plume. I use that in inverted commas. We think there's one there, but actually some people would say that there isn't. But essentially there was a weakness, and Iceland was part of that, although this weakness in our part of the world took place about 60 million years ago, when Iceland only came into existence about 20 million years ago. So this was taken during the Eyjafjallajökull eruption in 2010, and this was the Holarun eruption in 2014. Essentially, most people's ideas of a volcanic eruption is probably like a cone with lots of magma coming out. But in actual fact, in a lot of cases, some of the biggest eruptions on the planet have come out of cracks in the ground or fissure type eruptions, of which some of these fire fountains, like Roman candles, are of the height of Goat Fell, or 800 meters in height. And what goes up must come down. So if any one of these fire fountains stays in one place for any length of time, what goes up comes down, and it tends to form a cone. All right. So you get kind of central cones or central igneous complexes here, etc. But of course, running through it is a weakness in the crust, a linear weakness, and you won't be able to see those figures. But on the south coast, east, one of those is a vector, a line, and it's got 80, 80, 80, 80. In other words, about 400 dikes. I wasn't in the property market, but if I was 60 million years ago, buying an acre of land, I would have increased that by 10% today. All right, so that's the total crustal expansion in an east-west direction, with the intrusion of all this magma in that. And you think Arran's bad. You go to Mull, that's 170. You go to Skye, that's 500. It's amazing. Our students get tired of measuring them all and learning about them all. But of course, dikes are just conduits. I always think of a volcano like a plumbing system. And I apologize just after your dinner, really, but I always think of it's like the magma chamber. It is your tummy, all right? And sometimes, people say, oh, when's the volcano going off? Well, could I ask you, do you know, and I apologize for this, but do you know when you're going to be sick exactly? You know that there's gas in there, you know that it's rumbling, but you don't know when things are going to happen. But as that pressure builds up, that liquid magma leaves and comes up, and it'll work up. And as it goes through your intestine and stuff, there's horizontal bits and then there's vertical bits. And the horizontal bits are like this, which is the Dromadoon Sill, probably the second biggest in the United Kingdom after the Wind Sill that runs along the coast from Northumberland to Carlisle. This is the order of about 30 meters, and these are all beautiful columnar joints. And this goes for about half a mile, all right? It's exposed there, but it's actually also exposed down here and on the coast behind, because it was formed at lots of different levels. And there you can see our lovely example where you've got a raised beach there, and you can see this is a feeder dike. This is magma that's been coming up here and actually gone up and then spilled out there. And dikes intrigue me because the amount of pressure that must have built up, so the magma couldn't get up to the surface for some reason, but it spilled out along the horizontal weakness and it filled up that area. But in so doing, it lifted up all of the overburden above it, which at that time might have been about 3 kilometers. It lifted it all up to squeeze in between it. That to me is just amazing when you think of how much effort it is to lift your car up with your jack to put a wheel on. And that's what this magma is doing to that crust in this area. Okay. And this is an aerial view of your dike swarm with a few things around. So you can actually see the dikes didn't actually all go in the same direction. Some did, but some actually cut through them. So there were dikes at different phases at different times. We've got some that are locally associated with the spreading of the North Atlantic and a general weakness. And then we've got some that are locally to do with a local weakness, namely the intrusion of magma in a local balloon-shaped pluton, if you like, which causes a radial stress field. And out in the distance there, you might see another little island, Pladda, with a lovely sill on the top there and a raised beach. And in the far distance, Ailsa Craig, which is the cone of, if you like, a volcano there. All right, so some amazing pictures. And there's close up there with Pladda there, Ailsa Craig behind, and a lovely dike going out here. Some of them are olivine rich. They're called all sorts of things like tectonites and crinolites, and they're kind of basic to ultra basic. So that means that they came from deep down in the mantle as opposed to slightly higher up, although quite a lot of them are a lot paler than that and not so rich in olivine. But in the north, just behind where I'm sitting, I'm looking at this thing. If I look out my window, it's locally known as the Sleeping Warrior. And you see that because if you come out there, you come up the edge of somebody lying down with a helmet on, and that's his eye. And then he come along his nose, round his chin, and down to his Adam's apple, and onto the bubbles on his tunic. These are all kind of granite tours. And this is a beautiful arête or glacial ridge because the ice was all around it, and you've got a lot of frost shuttering, and the mere fact that that is so jagged means that the ice level during the ice age on Arran was only probably at this level, which is about 600 meters, and everything above was actually sticking out, like the Eskimos say, as nunataks, and these beautiful sharp edge ridges. But here's another example. This is the granite here, but you'll notice there's a bit of differential erosion going on there. That's what we call the Witch's Step of Cumnacalip. And essentially, that's a dolerite dike that's actually eroded out. And it's come later and intruded through the granite. Granite was already in place. It's intruded through it, but being less chemically stable and a smaller intrusion, it's preferentially eroded out. But it makes a really nice, interesting hike when you're going along here, drop down there and then have to climb up the other side. That's a picture taken from Goat Fell, and actually this was the ridge, although a little bit lower down, taken from the other side. So we've now come, we were in the north looking back south, now we're in the south looking north, and that ridge there, the Sleeping Warrior Ridge, has got a lovely rock step there, you can imagine, and a baby glacier, Corrie Glacier, would have actually poured out here over the edge there, the rock step, and down that glacial valley. And you imagine a small cirque-like glacier eating into the mountain of Kirvor, the Coxcomb, from this side and this side and this side. This is what's locally known as the Saddle. It's a passageway at about 1,200 feet where you can walk up one valley between the mountains. It's a col, or Bilach, and down Glen Rosa. So you're quite high up here. And this was earlier in the year when I was at that point. And I just thought, you know, it shows you the typical view of a lovely glacial valley looking out. And around about 20,000 years ago, that's your mainland over there. There would be a series of islands there of Cumbray and the Isle of Bute there. And this is the Firth of Clyde, which is kind of as deep there as we are high. That's about 200 meters deep. Some of the deepest water inside the UK continental shelf. And essentially the glaciers came down from Rannoch Moor and got diverted around the resistant peaks of the granite in the north and carved out this big deep trough here, and also one on the west coast known as Kilbrannan Sound. And they made us into our little island about 20,000 years ago. This you can see is the granite here, up here. But of course it doesn't quite finish there, because this famous gentleman, who you may recognise him, this is known as James Hutton, he's known as James Hutton, and in 1787, at the age of about 60, he actually came to Arran, and he came to Arran to prove that actually granite was igneous. Believe it or not, in those days, you know, so many people believed that all of the rocks we talked about this evening, sea turfs, granites, basalts, etc., they all formed out of the universal ocean, and they were all really sediments. And he came to Arran to prove that granite was igneous, because he'd heard that some geologists in the Alpine area had discovered some cross-cutting relationships, and they thought that granite was one of the older rocks of the cycle from the universal flood. So he came to actually prove that granite was igneous, which he did. And when he took a walk around, he actually saw this angular relationship of rocks, where you've got the older rocks of the Dalradian here, which, if you see here, would be the part of much larger scale folds that would carry on up into the air and down the other side. And then they've all been eroded down that point, the jagged ends of rocks like your soil. Before a soil was laid on here, which, because it was a tropical climate, is a kind of calcareous soil. That's why you might be able to see some of the little holes in this rock, which we call honeycomb weathering. And then you've got the red sandstones of the lower Carboniferous alluvial type rocks deposited on top. And when he came here, he looked at that and he said, the Earth can't be 6,000 years old, because it can't explain that, but he did say there was no vestige of a beginning or prospect of an end in his writings with Lord Elgin. So, you know, we had some foremost research, if you like, and the founding theories of geology established on our little island. And no matter what a lot of people say, everybody comes across the lovely unconformity at Sitka and the one at Jedburgh, but this is the first one. And he actually never named it as an unconformity, but of course it is a beautiful angular one. And to try and educate people and let people know, at our centre, we set up a public interpretation centre, and so a lot of these lovely boards are here, and we've got some leaflets that you can take out. You can either go out on guided walks or just take the leaflet and go out and enjoy it yourself. But as I was really saying, it's one island with many, many amazing stories. So I hope I'm reasonably in time, or I'm not quite sure because I haven't been watching me clock. Is that all right, folks? But come back up there. Ray, can you hear me?
All right, that's fine. That's fine, Stuart.
Oh, Ian, yeah.
I'm sorry, I missed the second half of your talk. My machine has given up the ghost, and I've had to come back in.